everyone, I'm Susan Nash, AAPG, and I'm just thrilled to be here and really, really excited to be able to share a wonderful presentation today on really cutting edge technologies that solve the problem of fracture interference, something that's really a definite worry for everyone. And this is part of our AAPG Academy webinars, and there are PDHs available. It just afterwards, I will be sending out an email with a link to the recording and also a link to where you can sign up for 1.5 professional development hours. There is a small charge of $35, so I didn't want to do it all together because it's confusing if we do it beforehand. At any rate, I just want to give a quick little plug to AAPG. This is a presentation that is being co-sponsored by the Energy Minerals Division and also the Division of Professional Affairs. If you are a certified geologist, you'll recognize that and want to encourage you to become a certified geologist. Also want to encourage you to attend IMAGE. Keep in mind that next week we will be having, next week will be our last day for discounts for IMAGE. IMAGE is the conference that we have with SEG. So I want to go ahead and introduce the presenters. We have Kevin Weatherich of Drill2Frac, and we will have a couple of people also substituting for Andrew McMurray, who couldn't be here, so we'll have those introductions in a minute. But I just wanted to go ahead and introduce you, Kevin, and let you get started. I will stop sharing my screen so you can share yours.
All right, thank you very much. And I am actually going to pass it off to Meg Dodge, who is our general manager, give a little bit of an introduction on what we're going to be talking about today, give us a background on the case study, and then myself and Tom Johnson will be talking through some of those key technologies we used in order to help this client along in coming up with some optimal strategies to mitigate and prevent the fracture-driven interaction. So with that, I am going to pass it off to Meg Dodge, who is the general manager here at Drill2Frac.
Thanks, Kevin, and thank you, AAPG, for having us. To get started, I'm going to review the high-level objective of the operator and just provide an area context background of the subject wells from the full study. Kevin, if you want to start the slides.
Should be going. Do you see it?
No, I do not.
Oh, sorry, maybe I forgot to share. Let's hold on. Zoom.
While you're getting started, I want to mention that it was really exciting to see Drill2Frac at URTech just the last month in Denver.
Yes, and the case studies that we're talking about today, one of those papers was just recently presented. So the primary objective, and this is the high level view, was for the operator to really develop an optimal completion strategy for the purpose of mitigating and decreasing their fracture-driven interaction risks. For the parent, making sure that they decrease the production decline that often happens with those interactions. And of course, always get the optimal production from the child well. On top of that, enhance their actual completion efficiencies during frac ops, and as everybody's goal, to maximize recovery for child and parents. In their first phase, what they did is they chose an optimized design and ran a comparison study and measured the results using additional diagnostics and real-time frac observations with some post-frac data correlation between everything provided from that original study. On phase 2, what they did was they actually took the successful—
money on other things that need more attention in this house. So I
know how she feels. So for phase 2, they implemented the design that was executed in phase 1. It was successful. So they implemented that design on all subject wells in phase 2, while also utilizing the real-time frac guidance. And they had additional diagnostics they used, but one other thing that they did test in that study was the different artificial lift methods, gas lift versus ESP. We are not going to touch on that today, but that was something tested, and those results can be found in that ERTEC paper. Next.
Sorry, just there we go.
So to get everyone oriented, the subject wells were located in southern Delaware Basin, as you can see in the map here. Target formations were Upper Wolfcamp and Third Bone Springs. The well spacing is relative to the child well to the parents, and that spacing ranged from about 1,000 feet to 3,000 feet. And the time on production of those offset producing parents also ranged from 1 year to 3 years at the time the child wells were drilled. So with that, I will pass that off to Kevin to get into the technical stuff.
All right, so yeah, what I'll be doing is talking about some of the setup of what we did and the technologies used and how we use those technologies. So I'll explain the technologies, show how we used it, and showed what we could do in order to get a better understanding of everything that was happening. So the first phase of this project was really to look at multiple completion designs. And we have a list of all the different completion designs up here. And you can see that they're color coded. So they did everything from 80 barrel a minute up to 100 barrel a minute. They went from 70 barrel a minute or barrels per foot of lateral to 85, and also tried different proppant concentrations or loadings, right, to see what the actual results are going to be. And again, remember, the main idea here was what can they do to minimize fracture interactions on the parent well, as well as improving completions. Now, the other thing that they did is they broke up this well. You can see here that they had 42 stages in total, and they broke it up with about 2/3 of the well using an engineered completion, where they actively were moving around clusters, trying to just optimize where they're actually going to place the perforation. The last third of the well or so, they just went with a purely geometric design, with one exception, which is in a couple of the stages where there was a really strong indication of being a pre-existing fracture connected to another well. They did do a little bit of mitigation around those, right? But in general, the first 26 stages all had an engineered design. Last 16 or so had geometric. And you can see rate ranges went from 80 to 100. We've got barrels per foot going from 70 to 85 barrels per foot, and proppant concentration changing. So where Drill2Frac came into this is one of the most important things when you're trying to figure out what's happening along your wellbore. You really need to understand the near-wellbore rock properties. And to do that, we use a term that we call the rock MSE. So anyone familiar with MSE, which is mechanical specific energy, it takes the drilling data that you collect on every single well and looks at the things like the torque, the RPM, rate of penetration, all of that sort of stuff to figure out how much energy is being used to drill each foot of rock. And the mechanical specific energy is really made up of two different things. It's the strength of the rock, right? Obviously, the stronger the rock is, the more energy it takes to drill through it. But one of the driving factors is actually the drilling efficiency. And that's why drilling engineers have been using this data to figure out, when there's bit wear, or if there's something else happening downhole, maybe with the downhole hydraulics, that could be slowing the drilling process. Well, what we as a company do is we flip that around and say, okay, if we can predict what the drilling efficiency changes are going to be based on looking at the drilling data, understanding what's happening, both on surface and downhole, we can normalize that out. And if we can get that to a unit number, then rock MSE is now proportional to the confined compressive strength of the rock. So this is a study area we're looking at. There was actually 3 parts to the study. There was this group of well over here, this group of well over here. And the first group we looked at was just these 4 wells where we had a child well, some parent wells, and a monitor well over here and over here, right? And those monitor wells were used to look at volume to first response and also do some microseismic interpretation. So one thing you'll notice is if you look at the colors here, we can see that as you get more into the red, that's low rock MSE, which essentially means lower strength rock. As you get into the yellows, that's typically higher strength rock. So in general, you can see that as you move east, rock was getting from lower strength to higher strength, but maybe a little bit of a trend going south as well. So right off the bat, you can see that there is some slight differences in those near wellbore properties. The next thing that we look at, and is something we've been doing a lot with our company lately, is looking for localized depletion. So when we take that rock MSE that we measure, what we found is that as you drill through localized depletion, it takes more energy to drill through that depletion. So here you can see you've got gamma ray, and I don't know why this is automatically advancing, but you see gamma ray, you see the rock MSE, and in areas you can see that the rock MSE is just jumping more than it should based on the geological response. And we can tie that back to localized depletion. So when we do that, we can actually map it across all the different wells. So the wells that have these little ticks on it, those are the wells that we believe have localized depletion. And you can see a few interesting things. First, you can see that in this pad, you can see how you get fewer and fewer depleted areas as you move further away, and that's to be expected. You can see that a lot of them match up to this azimuth, and you can pretty much tell where the well, where the fractures actually started from, right? So we could draw this azimuth, and this azimuth tends to be the maximum stress direction. We know that because we've got fractures combining together. So now that we have this information, we know what the rock strength is along the wellbore. This is the gamma ray, this is the rock strength, and here is the location of some of those depleted areas, right? So the first thing we do is if we're trying to design a completion to take this information into account, we don't like making wholesale changes to designs, but what we did is say, okay, knowing this, how can you adapt your current completion to take into account these localized changes in heterogeneity in the presence of pre-existing fractures? So one of the easiest things to do, especially if you have a well-defined area of depletion, you can see that there's a very high rock MSE here, probably related to quite a bit of depletion. In that case, what we did is we put a stage boundary right there, and that just gives us a little bit of extra room to avoid putting a cluster right there. So we segment the well up to make those stage breaks so that they not only straddle these areas of localized depletion, but we also look for changes in rock type. So you can see that the gamma ray and the rock MSE are changing quite significantly as they get into this new zone. But why not just put a stage break there so you don't have one stage straddling 2 different rock types? The next thing that we do is we look at where we place the clusters within the stage, because all things equal, we'd love to have all of our rocks with, or all our clusters in very similar rock, but they break down at the same time, take equal fluid. We want to minimize heterogeneity within the staging bounds. So what I mentioned before, if we could take a stage and minimize heterogeneity within the stage, that's something we like to do. We can place clusters in similar rock properties, right? So if we have them all in the same type of rock, they're more likely to initiate and propagate similarly. We can ideally place it in specific rock properties. So generally low rock MSC tends to allow all the clusters to break down at the same time and just gives them all a better chance of propagating the same. We like to avoid placing clusters in transition zones. So if you have a very quick change in the rock properties, you don't want to put a cluster there, because if you're off on your perforating by 1 or 2 feet, you could be in totally different rocks. We look into that. And we also try to keep all our clusters as possible, as evenly spaced as possible. So that's what we do to engineer our completion. A little bit different than what most do, but what we don't do is try to avoid big areas. Really, the only areas we'll avoid is putting clusters in around these depleted fractures. So the next step that we do here is we want to try to predict how our completion design is going to look. And we can do that through a number of different methods, but we built this model called FlowFX that looks at the real-time rock properties in the near wellbore that we get from drilling data. And we also look at the completion design. We look at your number of clusters, number of perf per cluster, hole diameter. We look at how they relate relative to stress shadowing, perf erosion, and all that sort of stuff. And this image here essentially shows you a bird's eye view of how we predict the fluid should be distributed, just based on one of the design. And the nice thing about that is one of the goals of this project was to try different designs. So what is the effect of going to 80 barrel a minute versus 90 barrel a minute versus 100 barrel a minute using just a geometric design? And then what's the same effect going from 80 to 90 to 100 barrel a minute using an engineered design? So what you're seeing here is a histogram of how the fluid is being distributed among the clusters. So if it was a perfect well, you'd have all your clusters at 100%, but this shows that distribution. And as you can see that as you go to higher limited entry, you tend to get a much tighter clustering of fluids taking a lot more, in that 100% range. And furthermore, if you go to perfrac and do some engineering, we can see even better improvement. This chart down here sort of summarizes it. We start with, on the baseline design, 47 clusters per 1,000. It went up just slightly with the perfect to 48 clusters per 1,000. And we can see that after we run the design, of the 47 clusters we shot per 1,000, about 33% of them are affected if you do a baseline at 80 barrel a minute. But if you go to perfect at 100 barrel a minute, we're going from 48 to 42. So we're getting a much higher percentage of our cluster being actively stimulated, about a 25% increase. And if you're used to uniformity index, we measure that too. In the original design, we go from a 25 all the way up to a 56 uniformity index. So it gives you a way to at least analytically understand what the effect of your different design changes are going to be. Now, another neat thing that we've started to do is that we can also essentially average the stage level changes within each stage. So here we have, it's only showing 27 of the 42 stages, I believe, for this well, just to, because don't really need to see all of it. And then we average the deviation information through here. So for example, is it going to be, look at the inclination, is it toe up, toe down? Was there a lot of dog's legs or a lot of steering in there? How much sliding was in there, right? All of this could potentially affect your completion. We also look at the average gamma ray, the average rock MSC as we measured, and LHI is the heterogeneity index. So how much heterogeneity is in that stage? So if you're below about 70, that's a pretty low heterogeneity stage. If you're about 150 or more, that's quite a bit of heterogeneity, and those could have a pretty big effects on how well treat. We then look at the mudlog lithology. And from there, we can sort of say, okay, anything that's a 3, those are stages that are a little bit out of the norm and could potentially have problems versus the 2s or 1s. So now let's bring all of this information and see how this helps in the case study. Now, remember, the key point of the very first case study was to understand the effects of design changes on the fracture-driven action. So we use diagnostics to do this. So what I'm showing you here in the very first image is from microseismic. This is how far the microseismic events went from the child well. And you can see that there's a clear bias for them heading towards the parent well. And this green line is essentially how much tracer was recovered in the parent well. So the tracer was pumped in the child well, and the parent well, we measured how much tracer they were getting back. And a few things become quite clear. So first of all, these colors are the different designs. So whenever they did an engineered completion using this design A, they really didn't see almost any tracers showing up in the parent well. However, when they used that same design in a geometric design, they actually saw quite a bit of tracer going through. Similar to this orange, yeah, they see some tracer in the parent well when they do engineered, but they see quite a bit more when it's geometric. Now, the one thing that does stand out is when they get to these high rates. So this one here is 100 barrel a minute. This one here is 100 barrel a minute. When they do geometric at 100 barrel a minute, you're seeing that they are finally not seeing as much flow from the tracer, right? So it's just a neat way to say that when you're doing engineering and using this sort of 90 barrel a minute, 1,700 pounds per foot, they're really not seeing any interaction between the wells. And these dots here represent where they saw depleted fractures. So we did some work to mitigate around those, and you can see that they really didn't have a big impact on seeing tracers, and that's because we mitigated around them. Whereas here, we didn't do any mitigation around those fractures. Another interesting thing I just want to show before I finish this off is this is the height growth from microseismic. So we're looking at, in this case, there was about 100-foot height growth below the wellbore, maybe 20% or 20 feet of height growth above the wellbore. And down here, you could see the areas that we identified localized depletion. And what's really cool when I put this together is you will see that where there was localized depletion, so you've already got some production from the offset parent, you could see that the fracs generally aren't growing as low. They don't have as much downward height growth. So this whole area here, you could see the only one that had excess of downward height growth was here, but we actually didn't see anything right there. We get into this area, you're seeing more downward height growth. As soon as we see our depletion, it starts losing that. And up here again, we see very low height growth, with the exception of this one that didn't have a fracture around it, right? So thought here is that where you have these pre-existing fracs, fluids going into them, and because the fluid's going into them, you're probably not creating as much net pressure. It may not go into it early on in the job, but it's probably connecting somewhere later on in the job. And because of that, you're just getting a much better, more contained fracture. So that's really phase one. That's sort of how we got to understanding what the best completion design was. Combination of doing the modeling, understanding how fracture grows, using our rock properties to improve perforation placement, and then also avoiding where fractures are going to be using depleted fracture identification. And the results of these were quite promising. When they found their optimal design, used it on the next well, they essentially found that the child well performed pretty much on par with the parent well, and also the parent well had minimal impact to its productivity, and within short order was able to be brought back to its original production. So with that, I'm going to pass it on to Tom. We talked a little bit about some of the pre-active stuff we're doing, and Tom's going to talk now about some of the proactive things they were doing sort of in phase 2 to build on this and do even more to help improve productivity.
Yeah, no, thanks a lot, Kevin. Now, just a quick introduction to myself as well to help this conversation continue. I'm actually traditionally a geoscientist, so you're going to have a geoscientist here talking to you a bit about the completions work that we're doing. And that's actually what I find really neat at ShearFRAC is that I like to think that what we're doing is what geosteering did to the drilling world. We're now thinking a bit more about geofracking. So Kevin gave a really great introduction there about some of the proactive measurements that you can get based on that rock and try and engineer around it and figure out the best way to get that near wellbore connection. And so then we went into our world thinking about, okay, how can we get a low-cost, non-intrusive measurement of how that frac is happening in real time, and then react to it, react to that rock. So here, that's kind of what I've tried to introduce here at the beginning. Again, I'm a geoscientist. I love microseismic. I love seismic everywhere. I'd love to have fiber optics on absolutely every single well. They give us some really great pieces of information, but they're very cost prohibitive. They're very difficult to analyze. They take a little while and they're not necessarily real time. So what we've created is this new measurement in the industry is this hydraulic pressure response measurement. And it's really relatively simple in its setup in that we have our own pressure transducers and we just put that on the wellhead. And we're looking at that pressure response on the active well and interpreting how that hydraulically connected wellbore all the way through to the rock is actually breaking that rock up. So we're looking at breaks in the rock based on how much we have pressure build up and how much we have pressure fall off. So if you're pushing on a rock and pushing on a rock and the pressure is increasing, you're not breaking it. If you create a large tensile planar fracture, fluid's going to rush into it. You're going to get a big drop off in pressure and a long time to kind of build it back up. So you can interpret these different ways of the rock breaking down, whether they're large or small breaks. And from that, you get a really accurate measurement of fracture surface area in real time. And when I say real time, I mean it's literally popping up in front of you so that you can react to it and work along with it. The other important thing about that here, which is where this work comes in really neatly with the offset fractures that Drill2Frac identify, is that you can put pressure transducers on any wells all around it. So now we've got this measurement of how the rock is fracturing with our hydraulic pressure response. And then if we see pressure increases on offsets, we get to see where those fractures are growing. So we've got a really, really neat insight in real time of how those fractures are growing. You keep going, Kevin. So that's really what our workflow is, and that's how we work through. So we have the Drill2Frac piece is a really, really neat piece up front to be proactive and give us these measurements. But even without that proactive piece, we're able to come in. Phase 1 is that live stream during field operations, being in the frac van, actively working with the completion engineers and reacting to how that rock is breaking, which I'll give you an example here in a minute. And now we've got a measurement of fracture surface area in real time. We're able to look at some of the traditional fall off data at the end of the stage and that production data later on to establish, okay, of that area that we created, how much of that is propped, how much of that is connected back to our wellbore, and to allow us really to see how these infill wells are going and give us some confidence in recommending fluid loading and proppant loading per well, really, really thinking about the development of that entire field. So we're mostly going to look at phase 1 into phase 2 here, and then Meg will come up at the end here with a bit of phase 3 results for this particular experiment in the Delaware Basin. So this is going to be a video. I want you to see how we are actually, how it actually looks in the data van. So this is sitting in front of the completion engineer in the data van. The top chart is the primary chart. So you'll see a white line go up and down. That's fracture density. And then a green grass grow, which is the fracture surface area we're creating. The two lower graphs, though, you can see at the bottom graph, there's a pink line that's increasing. That's the offset well that's actively being hit while we're completing this well. And then the middle graph there is actually the derivative of that line to let us know whether we're accelerating into it or decelerating. And so from that, you can see we have these green banners pop off across the top saying, hey, change your rate, change your proppant concentration. Let's really think about how we're reacting to that rock in real time and try and mitigate this FDI that we're seeing, this fracture-driven interaction that we're seeing. And so you can see here that we're increasing, we're fracturing really nicely the rock, but below we're hitting into this offset well. Our little circle on the right has gone red. So, okay, let's drop rate a little bit. We've got proppant concentration up to 1.75 pounds per gallon. How can we block off that runaway fracture and bring the fracturing back to our near wellbore? And you can see we're very successful with that, with the proppant increase, concentration increase and that rate drop. Very, very successfully able to mitigate that FDI and create more fracture surface area near your wellbore. So it's a really neat visual in the field to allow us to be able to see how we're fracturing and to really be able to think about not only just creating, just smashing in and creating a big fracture in the well you're working on, create that fracture surface area near the wellbore and try not to fly off and just smash into these parent wells that we've got all around us. So this is a great example of one of the stages on that particular project. I think if we keep going, Kevin. Here's just kind of a slowdown on it just to show you how sensitive this thing is. So again, the top chart is the primary chart. That's the measurement we're getting from the active stage. So we're pumping into, you see pressure, you see rate, you see proppant concentration, and then you've got our measurements of how dense of the fractures we're creating and how much area we're creating. But for this particular piece, look at the two secondary charts below. That bottom chart is the relative pressure. So that offset well will start at 0 PSI and increase or decrease based on that. And the middle chart is the derivative of that line. So you can see whether you're accelerating into the line or if you're decelerating. So you can see here, we know this is several stages in, we're immediately connecting with that offset well. So we're in and around probably one of these higher rock MSE areas, a depleted fracture that Drill2Frac have identified. And we know we're going to hit it. So we want to get up to rate, get our proppant concentration up, and then initiate our FDI mitigation. So you can see that second line, we've got ourselves up to rate. We're now dropping rate and getting our proppant concentration in, and we're slowing that offset hit. The really, really neat thing, and this is something that people have to see to believe. Here you can see halfway through the stage, we think, okay, I think we've got this mitigated. I don't think we're going to open up that fracture that's hitting that offset well again. Let's just try increasing rate by 1 barrel a minute. And immediately you can see there in that middle chart, we've opened up that fracture again. We start pushing on that offset well, and we panic in the data van and we drop that 1 barrel a minute again. So we're at 90 barrels a minute here, and we're literally going from 90 to 91 and back down to 90. And you can see how that sand concentration and that rate then closes off that fracture connected to offset well again. Back down it comes and we're level again. So it's very, very sensitive. And these are the kind of things that you need to have something visually in front of you to be able to see. And so it's something that we had in the data van, Drill2Frac's well level interpretation set up. We're saying, okay, we need to attack this stage pretty quickly because we're going to immediately connect and then we can mitigate it later on. And that allows us to really work out how to design our completions, how to optimize our completions to be able to avoid smashing into these parent wells, ruining them and creating a poor child well in that place. Keep going. So yeah, so that's that stage level. You can see how we're reacting to it in real time. You can get really into the granular pieces there. This is now taking a step back and looking at this well level. So the way to look at this is on the y-axis is stage 1 at the bottom, stage 36 at the top. On the left-hand side, the bar graphs are FDI magnitude from a child well to a parent well. And on the right-hand side is this volume to first response metric. That's super, super important. I've got a little inlay of how those things are calculated, so you can kind of look at it later on. But really the goal, and you see that we were able to achieve it here, is to reduce that FDI magnitude on that parent well. And that's that arrow on the left-hand side, just slowly dropping off as we go through the stages, but increase the amount of volume we pump into our new well before we see a pressure increase in that offset well. So now we're improving both things, right? We're improving our volume to first response and reducing that FDI magnitude. And that allows us we have to think of very, very creative ways how to be able to react to this and then come up with several different iterations. So where we landed at the end of here is really that optimized pump schedule. So it's actually, it actually takes a little bit of back and forth and learning on the fly with the data van team and trying several stages out with different iterations. But what we settled on here is that pad volume, especially for those wells that are near depleted fractures, that pad volume we reduced down. So we've got very, very little pad and we're getting our proppant in as soon as possible. And then we're ramping that proppant concentration up to a higher concentration quicker than we would have traditionally done originally. So we're basically trying to ramp in. We know we're going to connect, but we're ramping in and we're getting our proppant out there to divert our fluid away from that connecting fracture and back into our own wellbore. The outcome of this is that you do tend to reduce the amount of fluid you create. So this is hydraulic fracturing. We do still need fluid to create fractures. And so if you're just a well in the middle of nowhere, pump as much fluid as you possibly can. That's how you're going to get a good well. If you start to infill these wells, or if you want to develop an acreage, you need to design your spacing based on the amount of fluid volume that you want to pump. So the big change here was that, hey, we've got these big parent wells. We've got these 3 child wells coming in. We actually reduced the fluid volume by about 10 to 20%. And so up front, you got some really, really nice cost savings there. You reduce fluid volume, you're reducing the amount of water that you're using for that total pad. And you're also reducing the amount of time it takes to pump each stage. So you're much more efficient there as well. And like I said, this is detrimental because you're not creating as many fractures. But if you're infilling a well, you want to make that well as good as it possibly can be. So on this particular pad, this 3-well pad, we're able to save almost $500,000 on those 3 wells. So that's a really great upfront operational cost savings. Okay, so we have increased our VFR. We've saved a bunch of money and optimized our completion schedule. And what we want to see is, did we manage to stimulate that well as much as we possibly could based on the spacing we've got? So you get the next level there. So that's really where we start to look back at the pad from a broad overview. We integrate our reservoir engineering PTA method at the end to get some fracture half lengths. And then we're able to place fracture driven interaction, that magnitude and that VFR over the top of the wells and see where we saw most of this interaction and where we overstimulated or understimulated it based on reducing that fluid from 10 to 20%. So here you can see the accuracy or the usefulness of the Drill2Frac rock MSC log. As I guess if you just look at that child well, the bottom left one right now, you can see where we have white fractures, that's where we have larger FDIs. And you can see that that very much lines up with the yellow rock MSC, it's a higher rock MSC. We've got a more brittle rock, we're breaking into it a little harder, and we're creating more planar fracture initially, and that's running away. And so we have to work a little bit more on our FDI mitigation. Whereas definitely in that bottom, that kind of middle third of the lateral there, and that bottom left well again, you can see where the log goes red. And where that log goes red, we have very little leak off measured, and therefore very little fracture half lengths. And so we're perhaps understimulating those pieces. They're a little harder to break into. We don't see interactions on the offset wells, a little tricky to get into. So we've got to optimize our completions there as well. So we can be proactive looking at this rock MSC and work at a specific stage level, thinking about how that rock is breaking down. So ultimately, after doing all that work in this particular pad and particular experiment, the beauty of it was that we did have traces on each of the wells. So you want to go to the next Next page here, Kevin. Yeah, perfect. So we look at those 3 laterals again. We did have tracer data, and we ran our PTA method on it as well. And this gives us just, helps to build confidence in the amount of whether we stimulated it enough with enough fluid and enough proppant. And so what you can see here is that on the left, that's tracer data. We're just looking at that child well up on the top left-hand corner, and you can see that we get a lot of tracer data back, particularly that heel where we saw the FDIs, a lot of tracer data back within the pad. So that just helps us really build confidence in us seeing that we're stimulating these wells with enough fluid based on the well spacing that they came in at. On the right-hand side, the measurements of area that we get from the orange ones, the measurement of area we get in real time. So that area that we create, that area that we're propping open, versus the blue, which is that stimulated area that we're connected to. So the hydraulically connected area. And they should equal 1. We should create an area and should be connected back to our wellbore. And that's just a really 100% stimulation. And you can see in some of these child wells, we start to get that diversion. And so we start to see that we're perhaps potentially overstimulating those child wells a little bit. We're pumping a lot of fluid in. And some of that fluid is getting lost into a depleted fracture network nearby. And we're interacting with those offset wells. So bringing all these data sets together brings us some real confidence in that we're creating the right amount of fluid loading and the right amount of proppant loading. I think those are the real results that we saw correlating Drill2Frac and ShearFRAC data, and then Meg's got just the kind of conclusion results here at the end.
All right.
It's so exciting.
Thank you guys for doing that. So the services and data review today were, key contributors to the study. Some of the results as a result of utilizing the near wellbore specific properties and the FDI mitigation for risk reduction combined with the real-time active guidance and mitigation. The operator actually saw improved well productivity as seen in figure 1. Robert Gales had a question. I typed an answer about the history and time that was measured on that. So in the ERTEC paper, the most recently one written, I put the number in the answer. They have a couple of graphs that do show the measurements of production results that were measured. So you can dig a little deeper into that. They also received a shallower decline curve in the child versus the offset parent as a result of improved near wellbore fracturing and enhanced well uniformity. You see that in figure 2. There are also additional images similar to that in the paper as well. And as every operator hopes, money saving and overall improved reservoir productivity, right? The services today were key contributors, but not the only ones. So other variables that were utilized were HVFR, high viscosity friction reducer, well spacing, original frac design on the parent well, and the artificial lift test actually highlighting that the ESP was the winner. All those additional details are lined out in the referenced ERTEC paper. So we were not the only contributing folks to the success of their study. And I just wanted to close with that this was focused in Permian, but the cohesive approach is also being implemented by operators in Haynesville, Eagle Ford, and Montney Duvernay at this time.
Well, that's great. And okay, so I have a question. So one of the things that I find to be really interesting is that obviously people learn more about the well and the intervals as they continue to drill the laterals. So sometimes the first frac design is not the best, and the first lateral drilled is not the best, even though you think that would have the best results. So I like the idea of the mitigation, that like how often does it happen where the first couple of wells really had sort of poor frac design and you don't really have a good idea of the real capabilities productive capabilities of the well. And so how does your design help come back and like say, okay, this is what these fracs, if it's well designed, really should be able to do?
Yeah, so that's one of the nice things about our FlowFX frac modeling, right? Is because we know that there are probably as many design philosophies out there as there are completions engineers, right? And you throw in reservoir engineers who are doing completion designs as well. I mean, there's so much to choose from in figuring out what the best is. So that is one of the reasons that we developed our FlowFX model, right? Because it is an analytical model based on commonly accepted physics. So as a starting point, at least, especially if you're in a new area, you don't know where to start with, it gives you a great tool to say, okay, from an analytic, from a physics standpoint, what would be the effect of going to 6-foot cluster spacing? I'm just going to throw that out, right? And physics will tell you that that's just too close. You're going to have too much stress shadowing, and we can model some of that, right? What's the effect of going more limited entry versus less, the perforation side? Well, obviously that's going to affect your pressures. And so rather than just sort of throwing a bunch of spaghetti at the wall, there is some stuff you can do to model it, at least to give you that first level approximation. Now, anyone who's worked with models knows that no models are right, but some are useful. And that's really the goal of this, right? Is you model out some of the different options that you're thinking of, and you can get that first order approximation. And that's what this customer did, right? Based on that, they could say, okay, here are the 5, 6, 7, most promising designs, and let's just stick to those ones, right? And see how they perform.
Oh, that's cool.
Yeah. I'll just add my 2 cents there. That modeling statement from Kevin is the reason why we went into the measurement business rather than modeling business, right? It's very important to be able to come up with theories and come up with theories and think about ways that you can optimize completions. But then you need to know whether what you're doing is correct or not. And that's why I said at the beginning, microseismic data, fiber data, they're great. I'd love to have them on every single well. And the trouble is that's cost prohibitive. So if we can create a non-intrusive, a nice, cheap, non-intrusive measurement that comes in real time and you're able to react to it, that was really the goal of what we've done and what we've been able to achieve. So we've had people actively trying different things on the fly, and you're able to see whether it works or not in the moment.
Oh, that's great. Kevin, I have an idea. Like, okay, stop sharing and we'll have everybody, we'll be able to see people, and I want to invite people to turn on their cameras and open their mics and just go ahead and ask a question. So we'll have a sense of an open Q&A feeling.
And
Okay.
Susan, if you don't mind, there was a chat going on with Robert. Did I answer your questions, Robert, or did the progress of the presentation help provide clarification for you?
Yeah, Robert, go ahead and open up your mic and camera.
It was Robert, right?
Yeah, Robert Gales.
Yes, okay. And then if he doesn't speak up, we can move
Oh,
on
he
to
said
Pat.
yes. He
Oh,
said
okay.
it's fine. He's having a challenge with his computer mic.
Okay, great. Speak up or you can type over if there's something more you need clarified for that. And then Patrick, we can answer live. Do you want me to go ahead and read the question, Susan?
Okay, or if Patrick wants to.
Sure. In case he's having mic issues, I'll go ahead and read it. Does the hydraulic, oh, go ahead.
Go ahead and read it, yeah.
Does the hydraulic pressure response have to be corrected for lag time at surface, or is it instantaneous? I think that's Tom.
Yeah, it's pretty instantaneous. I mean, we do, as a general rule, the data in the field can be 3 to 5 seconds behind what we're seeing. So there is a time shift to make sure that the data lines up. So for example, a rate change lines up with a pressure change, and the rate change is obviously on the surface and the pressure transducer is on the surface. So So those are some things that you can line up. When you're looking at the fractures, we're not looking at this second, okay, that changes to this second, that changes to this second. We're looking at windows of time, and we're looking at pressure patterns. So think of it less of a microseismic moment point in time, and more as in, I'm now speaking to you, and these are sound waves, these are pressure waves coming out, right? And you can tell that I've got a low frequency, deep voice, and my amplitude is pretty high right now. I'm shouting to make sure you can all hear me, and I've got a strange accent, right? There's a lot of things you can interpret from pressure signals, and that's exactly what we're trying to do just with that hydraulic response.
That's excellent.
I'm going to steal that analogy.
Well, I have a question. Well, people, but anytime, feel free to open up your mic oh, so you have another question? Or, oh, David, you want to open up your mic and ask the question?
Sure. In parts of Reeves County, there's issues with a certain fracture set that induces a lot of water and also H2S. Have you been able to minimize any of that?
Those are projects that we've done quite a bit of work on, right? I believe you're probably talking about some of the lineament features. That's been a pretty active discussion, and we've done some work on that, right? What it comes down to is there have been many cases where we have been able to see that in the drilling data, right? Because if you think about what we actually do, is we're taking your drilling data and cleaning out all the drilling efficiency effect, right? So now we get a much better understanding of what's happening. So we have seen that those type of things sometimes manifest themselves a little different. Maybe it's sometimes we've seen something similar to what we see in our depleted fractures. We see just more energy drilling through it. Sometimes we'll see an effect on mud losses going through there, right? But once you clean up all of those drilling artifacts, right, and you're left with a clean response, we can look for anomalous data in there. And I guess really what I'm saying is that at this point, we haven't found a consistent anomalous signature to identify it, especially when you're starting to look through different basins. But if there is something, if something's reacting differently as you're drilling through it, it's something we can look at for sure and see if there's something there. So Meg, I don't know, what would you say our success rate is? We're probably at about a 50% success, somewhere in that range of detecting anomalies around lineaments.
Yeah, and that would be on the specific projects where the operator knows that they did in fact cross the lineament. We've had one project where they were unsure how deep the lineament went based off their seismic. So we did a collaborative study to see if some of our data and processes could help maybe identify if that lineament was crossing. And that was somewhat inconclusive, but what they're able to do in that situation, it was also a child well, right? So if they did frac where there was existing depletion, that's a super highway potentially directly toward that H2S. But by them optimizing their design, they had less runaway fracs. So they were able to have a little more confidence in not connecting, and by mitigating where the existing depletion was, some confidence in not, avoiding that super highway. So we don't always have the answer proactively in that situation, but we provide some analysis that can at least help them determine, how do we move forward? Do we have to skip this entire section of our wellbore where we think something's going on, or can we frac 100 more feet on each side if your data is showing any signs of that H2S, right? And when we've looked at those two, just to add to it, the operators tend to have a lot of other diagnostics. So even if we may not have a signature that we see in every spot, or the primary spot where they think there's H2S, we'll look at all 5 data sets that they have. And if there's 3 that seem to be consistent across, then it's like, okay, 5 would be the home run, it's there, but there's 3, so there's risk, and it helps the operator kind of do a risk assessment balance. So not always the answer, but can be a contributing variable depending on the other diagnostics they might have.
And we didn't talk about it here, but with that fracture identification, a lot of times you can differentiate between hydraulic fractures and natural fractures. They just look a little bit different, right? So if there is natural fractures around the liniment, sometimes we can find you those clusters, and if it's somewhere in the vicinity of where that liniment is, you might be able to get some insight into the extent of it, right? And how much lateral you need to avoid or change completion design or whatever the case may be.
Yeah, if there's some depletion associated around that liniment from an offset producing well, and your child well crosses it, that signature should show up.
Yeah, I guess from my side, on the reactive side as well, is there's different signatures that you'll get. So we've talked a lot about the interaction with offset laterals here, and those fractures growing away and hitting into it. But often, if you don't even have an offset pressure gauge, you can see when you're pumping into, I call it pumping into a void, right? Effectively, when you cross some of these larger lineaments, rather than that formation pushing back at you and you're allowing you to create that really nice dense fracture network, you'll often break into that lineament and you'll just be pumping into a void. So the pressure may fall off a little bit. You may actually get some issues with fracture closure. The number of fractures you're creating, that fracture surface area creating, we're just not going to be able to measure that as far as a hydraulic response, because there's nothing pushing back at you. So there are reactive ways to it as well, and we've had some success with that in Reeves County.
That's really interesting. Oh, sorry, I didn't mean to talk over you, David. Well, that's quite interesting. So that brought to mind a question that I had, and this is probably for you, Thomas. So I'm assuming your laterals are what, 10,000 feet laterals? Okay. So obviously you're going to have some lithological heterogeneity in there. And even though people like to think that, well, it's all going to, if you're at the same zone, it's all going to be the same, that never happens. So how do you accommodate that?
So our measurements we're just looking at pressure. We're just looking at the signal in the pressure and how that rock is breaking down. Mm-hmm. And so you can see a fracture in, I mean, as simple as a third bone spring formation that we see here versus a wolf camp formation, right? They're very different lithologies, even if you're not talking along a lateral, just within a well. We can measure a fracture down here and a fracture up here. You've got to take it to the next level. And when you say, okay, look, we're trying to improve the productivity of a well, a fracture in the third bone spring is going to produce a lot more fluid, oil, gas, water, than a fracture in the wolf camp. It's higher permeability formation. Right. You're going to get more flow into that fracture. And therefore that fracture is going to produce better than this fracture down here. So what we often see is the wolf camp wells will create more fractures than we do in these third bone spring wells, but they're not comparable. You can't compare one for the other. All you can do is make the particular stage, the particular well you're in, as good as it can possibly be. But ultimately, you're getting a measurement of that rock and how it's fracturing. Okay. And so, yeah, as you go along a lateral, we do get the geosteering, even without, if we were working without Drill2Frac, we'd still get that geosteering data beforehand. We'd look at that, be proactive about it. Obviously, having their data makes it's a lot easier to be proactive about these things, but you can be proactive about which way you're going in. And we actually, with our longer term clients, will set up 3, 4, 5 different completion types and say, okay, stage 1 to 3, we're going to ramp in slower, have a larger pad, and just ramp up to 1 pound per gallon. Stage 4 to 14, we want to get our proppant in as soon as possible, and we're only going to pump 80% of the fluid that we were at the beginning. We do actually, you can actually design it like that. And that really helps each stage to be as good as it can possibly be.
To elaborate on the heterogeneity piece too, the rock MSC takes the resolution of that actual near wellbore rock heterogeneity into account. So when ShearFRAC is able to have that variable information, They have also been able to identify optimal rock strength for fracture efficiency as well. So when you can marry those two and proactively know when you have a stage that's going to be more heterogeneous and potentially may treat differently, it allows ShearFRAC to optimize their active guidance, as well as understand when different responses are actually being caused by heterogeneity and rock strength versus potentially something else from the reservoir operation.
I really like that. And then, you know, like emphasis on the active guidance. I mean, it with all the different tools that we have that you're using, that just kind of the real time aspect is huge.
Yeah, I mean, I'm a geologist, and as geologists, we love being scientists and thinking about long-term things and going down. But my brain is very much operations focused. I drilled a couple of offshore wells, and they were fun to me, but they were fun because I was on the operations team. I went and did the shallow hazard assessment, and I went offshore and I drilled the well, and I could learn, you know, did I interpret the seismic right? Was I being a good scientist? And the trouble with some of those projects is they can take 5-10 years and you could never drill them, right? So you'll never know with interpretation you make. So that's why I love the unconventional world. And that's why I love drilling. I got to look at the seismic, interpret what I'm doing, say, hey, I think we're going to have to drill at 92 degrees, not 90 degrees here. And then I got to see whether I was right or wrong. And then the real frustration was I spent a lot of time interpreting where I was going to put it, drilling through it, spending 3 or 4 days sitting up at night, making sure that they were in the correct zone for me. And then I'd hand it to completions team and they'd just frack it all the same. And that was very frustrating to me, right? So now I was like, okay, how can I create the gamma ray log at the drill bit to tell me which zone I'm in? How can I create that measurement for the completions world? And that's what we've created with this hydraulic response. And that allows us to be reactive. It means we have to learn what moves, what changes in rate, what changes in proppant concentration. We have to learn all those things to what's going to make it an optimized completion, but we can do it now because we're measuring it. And we've got 4 or 5 years of experience now, so we know. And that allows us to put that active guidance piece in, and the computer can tell us what to do and tell the guys in the field what to do, and it really, really works.
Yeah, I think one of the things that we're working on between ShearFRAC and ourselves right now is how we can bring our near wellbore data into their database that they're already doing, right? So as you start seeing that, hey, every time I'm in this sort of rock type, the response is different, right? Then we can start understanding why the response is different, right? Is it because you have more competent rock? Is it because maybe it's more pliable? There could be a lot of things causing those differences. And by combining what we're doing, the real-time information with the pre-job information, just gives us so many more tools to actually understand what's happening downhole. And to me, that's where, you know, I think we forgot to mention it. We do have a technology partnership with Shear2Frac. We work very closely together on, you know, constantly improving our tools and merging the data set. So you just get a lot more information, being able to be reactive and reactive in a cohesive way to using minimal additional costs, no additional sensors typically, data you already have to make better decisions. And I know we're getting close on time, so I did kind of sort of want to end it up that that's really where I think the strength of this type of a workflow is.
Oh yeah, it makes total sense. Well, I want to thank you again, Kevin and Meg and Thomas for being here. And it's such an interesting presentation. And I just want to remind everyone that we are recording it. So when you get an email, you'll have it, have a link to the recording, and also I'll make it open and available so that anybody can watch it anytime afterwards too. So this is super exciting, and just want to thank you again, and look forward to the next one.
Thank you very much.
Thank you so much for having us,
Thank you.
Susan. Appreciate it.
Bye.
Cheers.
Bye.